All right, thanks, Brian. So I think one of the things I've noticed in the last couple of days is yesterday I decided there was a bit of a format explosion. We heard about at least 192 different image formats. And today I'm getting the impression there's something of a metadata explosion with all the different initiatives in the facilities and other places to create a lot of metadata. So one of the thrusts of my talk is going to be to try and get a handle on how we can think about all of these, get a handle on all of this variety. So just to set the scene, in terms of transferring scientific knowledge, the way things have happened in the past and are still happening today, one way of transferring the knowledge is the scientist writes a paper, it's transferred to another scientist in the post or through a publication, they read it and they understand it because they share a common ontology, they share a common understanding of the terms. So in this very simple example you can see, oh no you can't see, there's the abbreviation RA in that little table. And obviously whoever's reading it is assumed to understand what RA might mean. And without that shared understanding, nothing is obviously transmitted. Now when we come to using computers, we get another collaborator in this system, and that's those are the computer programmers that are also drawing on the same ontology in order to encode the information into the data file. So the data file is then transferred, the software at both ends understands something about what's in the data file, and then that is communicated to the scientist at the end of the process. Now it's very important to understand what I'm talking about here is software that's actually doing something with the data. So if all it's doing is it's passing along a text field, that's not what I'm talking about. That's essentially the process I talked about in the previous slide, which could have been mediated by a computer if it's just a Microsoft Word document that's being displayed. So I'm talking about software that actually does something with the data, uses the wavelength to calculate a d-spacing or something like that. Of course, this is a lovely simple picture, but in actual fact, as we've heard, there are all sorts of different formats. And the first comment I would make here is all of these different formats are going to be drawing on the same ultimate understanding of the world, if they're in the same topic area. But nevertheless, whoever's designed this format, designed this specification, has had to restate some of that ontology, restate some of those meanings. And in addition to having to grapple with the particular file format that might have been chosen to express that ontology. So what I'm on about here is to try and get a bit of a grip on this variety and try and simplify it as much as it can be simplified for the benefit of the programmers, perhaps first of all. And it is hard work developing ontologies, I think most of the people in this room would say. So I'd suggest a useful first step would be try and decouple the ontology completely from the format. And we know that is a very easy goal because obviously the knowledge that we transfer, the information that we transfer is not going to depend on the particular format we use. I mean, it's a blindingly obvious statement, but sometimes it's worth remembering that the knowledge has got nothing to do with the format. So let's focus first of all on our ontology. How can we express our ontology? Now this gets us into the domain of knowledge representation, which is rather esoteric, and I feel there's something of an impedance mismatch between us and the people that are working in this field, because as I tried to dive into the literature, it was quite difficult to understand what the point of what they were doing was in terms of, say, data files, which is what we're interested in. But there was a comment, it turns out, back in 1992 by one of the early workers in this field saying, oh, you could use this for data files as well, but no one's actually picked up on that. So one of the systems for representing knowledge that I think is particularly attractive for what we're doing is this concept of an O-log for ontology log. Now all that an O-log is, you essentially have classes of objects that are connected by a function. It's very important to understand that's a mapping, a mathematical mapping And ideally, you can actually read out a fact off this O log. So you can say an image is measured at an angle, right? Or an image has dimensions that are a pair of integers, and that this pair of integers has a first element that's an integer, for example. So that's the idea of encoding information in one of these ontology logs. And one of the reasons that they are, I think, they're very promising is because this is a very thinly disguised description of a mathematical category. And category theory, for those who don't know, and I certainly didn't know until I started looking at this, is a very abstract form of mathematics which has sometimes been called the mathematics of mathematics. So you can actually apply this type of description to different fields of mathematics, and the theorems that come out of category theory can then be applied to that particular field that you've applied your that you've described using category theory. And of course we would hope that was the case, because this is supposed to be a system for describing knowledge, and a mathematical field is included in that. And they're also very modular. You can obviously read that paper, which is more or less accessible, to find out more about it, and there are comparisons in there to other ways of describing other ontologies, such as RDF format, OWL, and relational databases. I should point out that those of you who have had anything to do with relational databases will probably see immediately that this looks very similar to a relational database schema because of these functional connections. One other thing that category theory, an important concept in category theory, is the idea of commutating paths. So for example, if we start at an image here, we can say it has horizontal dimension, an integer, and if we say that commutes with this path down here, we're essentially saying that the first element, when we describe the dimensions, is the horizontal dimension, which is a fairly trivial thing to say, but you can obviously extend this to much more sophisticated expressions. And these are called facts. In the O-log way of looking at things, this is called a fact that you can express in your O-log. So yes, what I'm saying is that our entire ontology can then be expressed as this set of concepts mapping domains onto ranges. And I think it's probably important to underline that the concept that we would think of as our data name is in fact the function. So we're making it clear that our concept is actually connecting one thing with another thing. That said, often we will tend to identify a thing not with the function. And of course we can always have an identity function, as I've drawn over here, and then we have effectively identified this class of objects as well. Right. Okay, so that's one structure, one way we can structure our ontology, which claims to be universal and modular. What does that mean for our data file? So if you've we've got a structure now for our ontology. How does the data file fit into this? So, given that we have a structure for our ontology, then our data file can do no more than give an instance of information from this ontology. There's no point in the data file restating the ontology, because we already know that. And given the way I've defined things, if the data file does want to change the ontology, then that will involve a programmer at one or both ends actually having to go in there and adjust to that new ontology, which is essentially excluded from this scheme, if you like, because that's essentially going back to the old way of doing things first. Therefore, all that our data file is providing to us that is important is going to be attaching values to concepts. And given that we could have multiple values for a concept, so rotation angle, for example, given that we can have multiple values, that means we need a way to match up. If we have multiple concepts with multiple values, so we've got an image, we've got rotation angles, we've got many images, many rotation angles, the data file has to be able to match rotation angle to image. And that's all we need from any data file, those three things that I've put up there. So let's just apply these ideas to a simple format to start with, a CIF file. And we can see this very simple mapping, a concept in our ontology log. is just a data name. So one of those functions is just a data name. The value or values attached to that data name is either just the value next to it in the data file or the column associated with it. And the correspondence between values when you have more than one is going to be having the same column index. And we're done. So we can, from this point of view, we can say, well, the actual grouping of these data names that the CIF format enforces is not telling us anything new. And of course it isn't, because that's already stated in the dictionary. We already knew that. But it's syntactically important. Now, I'm not going to dwell on this too much because it's much more complicated. The slides will be available for you to think about, and it gets quite involved with tree structures depending on what aspects of your file format you've used. But the essential idea is that you identify a concept with either a nexus class or the leaf node in the class, or an attribute. As far as I'm concerned, attributes and leaves are essentially the same thing. And then you can collect together all the instances of these, and they're your values. I won't go into detail because, first of all, we have an existence proof from Herbert's work with the image CIF and NXMX mapping. And second of all, there's a very convincing discussion in this book this reference that I've given down there, describing how any data structure is going to be a relational data structure plus something else. So I don't think there's any argument about this being possible. Now, just going back a little bit to our diagram, we've got a function mapping A to B, and we say that B depends on A in that case. Now, if we start to think about this, well, if we've got our calculated structure factor, that depends on a whole lot of things. Does that mean we somehow have to list every imaginable thing that this could depend upon? There are two answers to that. One answer is, well, if that's the way things are in the real world, that's the way things are in the real world, and whether you list them or not, it's still going to be true. So from that point of view, well, it might be good to list as much as you can. But in terms of the data format, you really only need to list the things that actually change in the data format. So going back then to describing your metadata, doing your ontology, you can list all the dependencies that you expect might reasonably be used in a data file, or add them on later. As I'll explain, that's not an issue. So I talked about, I mentioned a data unit here in the last point, and let's see if we can pin down what this is more precisely. And this essentially echoes what Andy spoke about yesterday with the ESRF work. We can define a data unit in terms of our ontology as the set of data names that do take multiple values within that unit. And that's essentially equivalent to saying the set of data names that don't change within that unit, but you don't necessarily know what. It's very hard to identify that because it's sort of it could be seen as an infinite set. That phase of the moon doesn't change, for example. So then, to specify our data unit, all we need to do is specify the items in our ontology that actually change, and I think that's a fairly obvious point. So if we're just rotating the sample about one axis, we say rotation angle. The rotation angle defines our data unit. If we've got multiple samples, multiple axes, multiple angles, then we have to list all of those. And I think that's restating the obvious in a way, because that's how we all understand a data unit anyway. So now we're in a position to talk about the overall framework that I'm talking about. And I don't want to give the impression that this is a new framework. What I'm saying is that any framework can be analysed in this way. So I'm not in any way saying that you have to do things differently. I'm saying that it may be helpful to look at your data transfer framework in this way. So we have a catalogue, which is our list of concepts. We assign some sort of canonical name, and we describe the range of values that that function maps to. And we identify all the names, the other names that it depends upon. So that's essentially the domain that it's mapping from. I've said that units don't matter at this stage. Units don't matter for the catalogue, you just give the dimension, so it's length. And that avoids all the arguments that really are pointless as far as the ontology goes as to what the best units are. And you give maximum freedom to the users to decide what's most, what's used in their community. And just as a sideline, often we have, certainly in CIF, we might have a sort of a small finite set of values that we think something can take. For example, there may be a set of refinement flags that we recognise, so these should obviously also be listed in the ontology. The actual values that you choose are not as important because the next stage you'll see you can decide how those are going to be represented in the actual format. So we have a catalogue, and that catalogue is intended to apply to any format. And then we have what I've called a format adapter, which explains how the items in that catalogue are actually mapped into a particular data format. And so you have to obviously describe how to locate the values, how the actual types in your ontology are turned into types in your format. And I didn't mention that before, but in your ontology you're going to be talking about real numbers, complex numbers, integers. But when you go to your data format, you're obviously going to be realising that in some way on the computer. You may be using a text string, you may be using 64-bit floating point or something like that. So that's the sort of thing that you would put in the format adapter. Importantly, you say which items, which dependencies of your canonical names are actually expected to change. And this is one way that we actually future-proof our data format, and I'll explain that in a minute. So here's an example. This is in no way a diffraction data experiment, so it's perhaps not as appropriate, but we haven't seen any EXAFs yet, so this might be fun. I was a participant in a working group to define the EXAFs data interchange format for a while, which was one of the things that provoked me to start thinking about this. And what the group eventually came up with was a glorified 3-column ASCII format with the interesting twist that the content of the columns could be specified dynamically in the header. So you might have had transmission fluorescence, or you might have had transmission absorption or fluorescence absorption, and the header told you what was going on there. So the catalogue, I've given one example of an entry in the catalogue you might expect to see. So it's that's probably sufficient to define exactly what you mean. And then an adapter document, we might have a little table saying how to extract the values of items in the catalogue that are present in the format. There's no reason to use everything in your ontology. That's up to the person defining the format to say what they would like to be in the ontology. You can see that there may be some things that are not obviously present in the data file, but are necessary. For example, the scan step. In terms of a functional relationship, sometimes you can have an energy measurement in EXAFs that comes out at exactly the same measured number. So you need to distinguish those two by some sort of a step number. And you explain the data unit and how your values are going to be represented. And this doesn't have to be a long document. You can imagine for perhaps, I would guess, 70% of the 192 image formats, you could imagine that this document is going to be quite short because the actual syntax of the files may be identical, but one or two different data names are present in the header, and that's how it is considered to be a different format. And for CIF, it's even easier to do. I don't think I really need to explain this very much. And there are no data names for EXAFs yet defined in CIF. All right, so what are the benefits of doing things this way? I won't go through all of them, but one benefit I think is worth underlining is that up until now, because the development of the ontology has tended to be done by people that are actually working on the data format as well at the same time, the development of the ontology has been restricted mostly to people that are computer programmers or have a lot to do with computers. And this excludes a lot of specialists in the field that have a lot to contribute. So I think if we come up with a way of specifying metadata that is simple and accessible but does not rely on any knowledge of computers, we can draw in more people to do this work. I mean, I know I've said that we seem to have too much metadata, we seem to have an explosion of metadata, but at the same time there is still more metadata that is needed for the different fields. And obviously it does free up the data framework designers to choose whatever format's suitable for them, because it's work that's done independent of the ontology. And we keep anything to do with format, obviously, out of the ontology. This is something that sort of ties in with what Andy was talking about at the ESRF, this middle point here, that we can say in crystallography, we're used to thinking of scanning all of the indexing the peaks with HKL, and then that sort of defines our data unit. But there are experiments out there where you might sit on a single peak and vary some other parameter. And that is now able to use exactly the same ontology, it's just they're going to be varying something else. HKL will be constant, but energy will be, the data unit will be defined by the energy changing. And the ontology doesn't have to change in order to accommodate that. And this is probably something that's quite relevant to what we've seen, is that these are very modular ontologies. It's relatively easy to join them together. And there's a theorem that is mentioned by Spivak and Kent in their paper, saying that there will always be a functorial transformation, I love that word. So you will always be able to transform one O-log into another O-log in a way that preserves the facts, that preserves the commuting paths. That sounds sort of useful. It's essentially an existence proof. In actual fact, there may be many ways to make this transformation, so it's not completely solving the problem, but it is giving us some guidelines to say that, yes, we can, rather than try and have one uniform ontology, we can actually imagine defining transformations between pre-existing ontologies. And I think that's probably going to be the only way to go, given the enormous ontologies that we've seen today from the different facilities. We're probably going to be far better off finding the transformations rather than redoing the ontologies altogether. I'll skip that. Here's a little example of how we might expand the ontology without actually affecting our data formats. So this is drawn from recent experience. The original idea in a CIF file is that our calculated intensity depends on the HKL index and lots of other stuff. Then we discover twinning, in which case our calculated intensity is now going to depend not only on the index, but it's also going to depend on the particular twin that this peak came from. And that will have some mass fraction which we'll need to use to calculate what the structure factor is. So if with this we've added in twin as a dependency of the calculated structure factor, and this does not affect any data files that were constructed according to this ontology, because by default anything that's not explicitly varying in that file must be constant. So the twin, there was one twin and it was constant. Perhaps more interestingly, if we start producing data files that conform to this ontology, we can still transform back to this ontology by simply choosing a constant twin value and splitting it up into separate data files, each of which have a constant twin. And I think this is a very general operation in terms of moving between different representations of the field, or as the field expands. So I'll just finish off by discussing a few applications of this approach. The first clear point, I think, is that we can have a universal programming interface for extracting values from a data file. Essentially, we need to simply get the values, give the name, the location that matches our concept, and a type from the ontology. So we're talking about a real number rather than a float 64 number. And of course, depending on the programming language you're using, you may have to specify the type. You may have to have a type-specific version of this function. And that's all we need. We've got all the values. But of course, for convenience, we're probably going to probably going to want to define a few functions like this, for example, an iterator, so that we don't have to get all of the images all at once. This is also a very useful function in terms of just taking the value that corresponds to some other value. And that's it. And such a function would actually tell us a lot about the way the data are stored in that particular data format. So one suggestion I would have is that when writing a format adapter description, some pseudocode for how such a function might work would be very interesting. Would be a very nice specification of how the data are stored. You'll note that we can't really go the other way and say write a set values function, because that is going to involve format-specific information, and it may change from day to day depending on what the intended application of the data file is. And this also leads us to thinking about some sort of translation between data files. We can use that getValues function to just get our concepts with their associated values. We can apply some transformations, simple transformations based on what we know about how these are related. And at this point I would like to point out, it was mentioned yesterday, there's the language DREL that's been developed for the new CIF transfer framework is actually very well adapted to describing these types of transformations, and that's something that we're going to be looking into in the near future, or something I have been looking into, as to how we might describe these transformations using DREL. And then the final stage is going to be somehow encoding our transform data according to the way the format wants to do it, and that's obviously going to be format specific, as I said. On this topic, I'm saying this step here involves semantically irrelevant format specific structuring rules. I like that separation of scientifically meaningful from useful for other reasons, because sometimes people get a little bit involved in their data formats and think that perhaps some structure in their data format is relevant or carries some sort of scientific information, and that needs to be clarified if that is the case. And you'll note I'm not advocating for any particular data format here. Quite the opposite. I'm saying that you're now free to choose the technically most efficient version or format for your particular application. And we've heard a little bit about concordances. Obviously, Herbert Bernstein and others have done an enormous amount of work to produce this concordance between ImageCIF and NXMX. My imagined concordance would be somewhat simpler than what they have done, because they're managing to preserve all of the nexus structural information as well. And you could imagine a minimum concordance would just have a list of equivalences between the data names appearing in both formats. And a more full description might include functional transformations and other useful information. I don't think that's. I think that's sort of pretty obvious. I don't think I'll go into that. So I'd like to finish off with just a few proposals that come out of this. I think it would be good to have a metadata concordance, which is going to be relatively easy. Given what we've heard today, I don't think it's reasonable to expect that any one person or even any one committee would be able to maintain such a concordance, given the vast number of metadata that's around. So I think we should be looking at instituting something like the way the semantic web is supposed to work, so that individual workers can link their metadata to other pieces of metadata out there, not necessarily doing it comprehensively and not necessarily even linking all of their data, and then web crawlers or web agents could then go out and match things up in a sort of an ad hoc way. I think it's very important to, especially for the DDDWG, to define exactly what it means by metadata. What is sufficient information for metadata? And I suggest that these 4 things are sufficient, and there's no need to go any further. On the same note, I think it's extremely important to keep format-specific elements out of the metadata definition itself. And as I said before, I think get values, the pseudocode for the get values function is very helpful if you're talking about a particular format. And so to finish off, I'll just acknowledge some of the where most of these ideas came from. I don't feel like there are many original ideas in this at all. Obviously, I've mentioned Herbert and others' work on that on the concordance, which is an enormous amount of work and got me thinking about some of this. There are the publications of Spivak and Kent, which they've tried very hard to make it accessible to non-mathematicians. And obviously, the relational model for databases has flowed into being part of the CIF world for quite a long time now, and that's informing some of what I'm thinking about. I've mentioned DREL and DDLM, and there were lots of interesting discussions on the XF's format development list when they obviously didn't have a clue what I was talking about. And in retrospect, it's probably true that I didn't know what I was talking about, but it provoked me to try and clarify my thoughts. So I'm very grateful to them for that. And obviously I'm very grateful to ANSTO for supporting this work and letting me come here. So thanks.
Thank you very much, James. Are there any questions from the floor?
I'm not surprised.
Are we able to hook up a Skype session immediately?
Are there any other questions that...
Are there any other questions while we're looking at that?
So I have a bit of a surreal feeling that I've been listening and watching something different. So you use the colourful words explosion of formats, yes, explosion of metadata, all the different facilities ontologies.
Yes.
Now, my reading of what I've witnessed is that, apart perhaps from MX, is really some excellent work going on with respect to, and we heard, say, from the High Pressure Commission, a very specific set of metadata terms and to me a lot of progress in bringing that together, which will, I mean, you can never prevent diversity, but at least it's a clarity of what the IUCR Commission on High Pressure thinks. We see the publications from the XAFS Commission are already out there, the publication from the Small Angle Commission is out there. We have in any case the de facto success story, the chemical crystallography sieve. Now, the extension to raw data is the task, and that is, still to be defined by the Commission on Structural Chemistry. So, in a way, where do we agree? I suppose I agree that the MX shows diversity, and to table that I would invite the chairman of the Commission on Biological Macromolecules to comment on how he would like to see the management of the diversity to hopefully arrive at some degree of convergence. Anyway, we'll come to that in a moment, and we'll take Herbert's input where he aligns, I've learnt by email, with what you're reading of the situation. So, am I being naive? It's my problem of not understanding the complexity that you have witnessed over many years with the comp-sieves. What am I missing here?
No, well, I mean, if you take, for example, I wasn't thinking so much of the high pressure work. I was thinking of, say, the ESRF work, these enormous lists of metadata. Simon's work in Southampton, he's got more enormous lists of metadata.
They're all very specific, manageable,
in
proper,
their own worlds, yes,
respectable items that are needed. Absolutely. There is no explosion here. It's a finite thing, and these are needed.
I'm not saying they're not needed. I'm not saying they're not useful.
But
what I'm saying is they're in their own world. How can we incorporate what Simon's done into CIF? How do we do that?
Well, you tell me.
Well, I am. Well, I just... This is sort of the thrust. This is the thrust of my talk. Is that?
But this is a clear list
from. Sure. So someone's got to sit down there and bring that into CIF.
I mean, the
and find the overlaps. Find, there may be, and also, I mean, Simon's done things in terms of the RDF. I think that's right, isn't it? Yeah. And now it is possible to transform an RDF representation into this ontology log representation. I would say that this is a more efficient way to express an ontology when you have multiple values. When you've just got a tag value set up, and so this was prepared by this person, then there's no particular advantage in doing it this way. So you have these types of mismatches when you actually want to try and incorporate stuff in.
It's a clear list, it's a long list, it's
Yes.
not an explosion. That's my point.
Oh, okay.
Now, the formats problem, explosion of formats, we discussed that obviously after the day yesterday.
Yes.
And there was the wish for a standard format, and clarity was driven, and we have heard today about Diamond wanting to still arrive at the Nexus standardized format. So there is elements of wanting to arrive at a standard format, but nevertheless there is still a growing diversity. But the data processing software people are managing that diversity. It's not an explosion.
Well, I mean, Vladek might want to comment on that. I mean, he's obviously managing it, but first of all, let's...
My point being on the word the semantic aspect of the word explosion, it is a colourful word
Yes.
that is trying to imply not managed. And I think that's not fair.
Okay, all right, okay. I'll take that point. It was perhaps over-egging the pudding. But there's certainly a lot, I would say there's more work is being done than needs to be done, simply because it's not being managed as well as it could be.
Yeah,
yes,
duplication.
yeah.
Must be avoided.
But I need to pick up that point you said about Diamond moving to Nexus, and that's a single format. It's only a single format in the sense of it's all HDF5. But as soon as you have a different scan axis, you have a different format. And I mean, I haven't spoken to Vladek, but I think that's what he meant when he said there are 192 different image formats. It's just maybe there's one entry in the header that's different. So the syntax is the same, but it's a different format. And the ESRF are not producing just one Nexus format. They're producing 20, 30, 40. And a programmer, and the reason they're different formats is a programmer has to actually program for each one of those different formats as far as the semantic content goes. If they're just passing it through to the user, then they don't.
Agreed.
What I meant by 192 formats, they were really 192 frame formats plus goniostats. Yes, we have different description of the goniostat, and you have 4 or 5 possible goniostats.
Right, so that's a semantically...
Yes, so you see that we are only taking handles from the header, and there is always one of the 5 possible goniostats, and you have zeros of the goniostat is also defined in dev site.
So this is
dev site file. So you see that basically my point is that if you have dev site file for HKM, if you have dev site file, you can process any data from virtually any synchrotron station or home source. Now you may have something special, and we, from time to time, we have something special. But the real problem is that the configuration on many beamlines changes. And people even do not know that they are changing configuration. Yes, they are doing various things. They do not know that this affects the processing. They find some way to do that to work for their beamline, but it not necessarily works for another neighbor of beamline, which has exactly the same goniostat and exactly the same detector. I do not know how this can be solved. Yes, I mean, when we are talking about universal format, before we will start to rewrite everything what was collected into this new format, we should have this new format on at least 60, on half of the beamlines all over the world. I think that it's almost impossible.
Yeah, I mean, I wasn't talking about a universal format. I was talking about a universal metadata
or universal metadata.
Yeah. So that's
Yes, but you see that in fact, there are two types of metadata. One type is from single experiment. Yes, we have single experiment, few data sets from single experiment. And we can derive some metadata from this experiment. But this will be very limited. But if you have, let's say, 1,000 experiments done on this beamline, you can derive some expectation when your crystal will die. And we have done that on 21 ID. Yes, we put the effort, we made very many experiments. And basically, if you are giving the composition of the sample now, you have some feeling when your crystal will die. Yes, when radiation damage is such that you cannot continue. And it depends, obviously, many factors. But one of these factors is the temperature at the sample. And if you will look at the PDB, do you know that temperature of the sample is not correlated with a beamline, is not correlated with anything else but PI. Yes, so PI, there is one PI which always collects data in 113.5, no matter on what beamline he is. He collects the data, yes? Somebody put 113.5. Yes, but if you will look at the crystal decay, you can say something, but not on one set, but on many sets. You can say something also about the quality of the cooling. And if chairman will allow me to say one anecdote, but this is quickly, yes. But you see, I used to consult for one beamline, I will not mention it, and they were very proud that they have phenomenal intensity because crystals are dying like hell. Yes, and at some point I brought lipoxygenase, the crystal which I knew very well, and I found that intensity is not very high, but really the crystal is dying very fast. So I asked what is the temperature of the sample in the place where is sample, and they told me, oh, it's 100. And I said, can we have thermocouple? We do not have thermocouple. Can we take from control room? Oh, no, there is no way to do that. There is no need to do that. Why? And you see, in the end, I spent around $100. We drank a lot of alcohol, and when we came back, I forced them to go to the control room to borrow thermocouple. It was 140 Kelvin. So it was fixed. Next time I came there, it was again 140. Yes, guys.
So the point being that just because something is in the file as metadata doesn't mean it's true. Yeah. So there's going to be a point of decreasing returns. I can see that where you don't want to.
But you see that what I am saying, that fixing the cooling device is one of the 5 beamlines, which each cost $3 million per year.
So I think that's a very valid point made. And of course, I suppose the point about metadata is not just values, but it's intimately bound up with relationships. And one of its main functions, I think, is as validation. So I'd like to give Herbert just this opportunity, using a slightly low-tech version, to come in over Skype. He's happy to type his comments if James will speak to them. I just want to say, says Herbert, I agree completely with James. Not quite completely. My only disagreement is that we will need our right values pseudocode suggestion for each format. Want to respond to that, James?
So, as I understand the question, Herbert thinks that a right values pseudocode would also be good. The only reason I left that out was because I felt that you wouldn't necessarily know for a given format how you wanted to use that format. So the concept being that the reason you're using a different format is because that format gives you some advantage in terms of efficient transfer or efficient storage or some other non-ontological reason. And so it may well be that you could use the same format and the same ontology, but with a different purpose, in which case you might want to store the data in a slightly different way. That's the only... and therefore you couldn't write a universal right values function. But you could imagine writing a few to say, well, this is if you want to have a minimum size, this is if you want to have a fast transfer. I'm thinking of a sophisticated format here. I think in the case of CIF, there's only been one way to write it, but I suspect in Nexus there are quite a few ways that you could write a consistent Nexus file.
So is that an adequate response, Herbert?
We'll see if we get a comment back. It says away. It says away at the top.
It's gone away. Just while we're waiting, I suppose one point about a pseudocode function is that it does not need to be too specific. So there may be circumstances in which your pseudo writer simply gathers together the necessary information you want to combine in an output.
Yeah, I haven't attempted to write one of these. I've attempted to write a get value, but I haven't done the other one.
So Nexus in particular has strange write rules.
No argument from me, Herbert. And you would know much better than I.
Links and such required.
Yes, I mean, an interesting point that's probably a little bit too specific for this is that if you are linking data to somewhere else, that's implicitly saying that the parent group is not relevant. That's an interesting point that I would make, is that making a link means that you don't really care what the parent group is. But I mean, I think that's a conversation for me and Herbert to have rather than for everyone here.
So my feeling is that the difficulty in communicating at this level suggests that this is a conversation we could very usefully have online in one of our forums.
Well, I don't agree. I don't see your point, Herbert, that you would need extra metadata in order to write those links. I would have thought those links are specific to the Nexus format rather than being something to do with with scientific knowledge. I mean, that was the point of my statement, that the information doesn't depend on the format. That scientific truth or scientific facts don't depend on the format. So you can't say that because you put a link in there, you've somehow created some scientific information that wasn't there before.
So let me wrap up the discussion at the moment, because time is against us. But Herbert agrees on that comment. So thank you again, James, for very stimulating. So I'll hand over to my co-chair and ask if I have a few moments to give a presentation.